Hi, in this video we will talk about intent classifier and slot tagger in depth. Let's start with intent classifier. How you can do that? You can use any model on bag of words with n-grams and TF-IDF, just use classical approaches of text mining. Or you can use some recurrent architecture and you can use LSTM cells, GRU cells or any other. You can also use convolutional networks and you can use 1D convolutions that we have overviewed in week 1. And the study actually shows that CNNs can perform better on datasets where the task is essentially a key phrase recognition task. And it can happen in some sentiment detection datasets, for example. So it makes sense to try RNN or CNN or any classical approach as a baseline and choose what works best. Then there comes a slot tagger. And this is a bit more difficult task. You can use handcrafted rules like regular expressions so that when I say, for example, take me to Starbucks, then you know that if something happens after the phrase take me to, then that is most definitely like a to slot or any other slot of your intent. But that approach doesn't scale because the natural language has a huge variation in how we can express the same thing, so it makes sense to do something data-driven here. You can use conditional random fields, that is a rather classical approach, or you can use RNN sequence-to-sequence model when you have encoder and decoder. And a funny fact is that you can still use convolutional networks for a sequence-to-sequence task as well. And you can add attention to any of these models, any sequence-to-sequence model. In the next slide, I want to overview convolutional sequence-to-sequence model because that gains popularity because it works faster and sometimes it even beats RNN in some tasks. Okay, let's see how convolutional networks can be used to model sequences. Let's say we have an input sequence which is padding, then start of sequence and 3 German words. And what we actually want to do, let's say we want to solve the task of language modeling. When we see each new token, we need to predict which token comes next. And usually we use recurrent architectures for this. But let's see how we can use convolutions. Let's say that when we generate the next token, we actually care only about the last 3 tokens in the sequence that we have seen. And if we assume that, then we can use convolution to aggregate the information about the last 3 tokens, and this is the blue triangle here, and we actually get some filters in the output. And let's take half of those filters and add them as is, and the second half we will pass through sigmoid activation function and then take an element-wise multiplication of these 2 halves. What we actually get is we get some gated linear unit. And we add a nonlinear part to it, and it becomes nonlinear. So this is how we actually look at the context that we had before, and we predict some hidden state, or let's say next token, and you can use convolutions for that. And then that triangle is actually a convolutional filter, and you can slide it across the sequence and use the same weights, the same learned filters, and it will work the same on every iteration on that sequence. So it is pretty similar to RNN, but in this way, we actually don't have a hidden state that we need to change. We actually only look at the context that we had before and some intermediate representation. But you can see that we actually look at only 3 last tokens, and that is not very good. Maybe we need to look at like last 10 tokens or so, because RNNs like LSTM cell can actually have a very long short-term memory. Okay, so we know how to, from convolutional neural networks, we know how to increase the input receptive field. And we actually stack convolutional layers. Let's stack 6 layers here with kernel size 5, and that will actually result in an input field of 25 elements. And the experiments show that 25 elements in the receptive field might be enough to model your sequences. Okay, let's see how CNNs work for sequences. The authors provided the results on language modeling dataset, which is Wikitext 103. And you can see that this CNN architecture actually beats LSTM. It has lower perplexity, and it actually runs faster. We will go into that a little bit later. And another example is a machine translation dataset from English to French, let's say. And there they have a metric called BLEU, and the higher that metric, the better. And you can see that convolutional sequence-to-sequence actually beats LSTM here as well, and this is pretty surprising. What is a good thing about CNNs is the speed benefit. If we compare it with RNN, the problem with RNN is that it has a hidden state, and we change that state through iterations, and we cannot do our calculations in parallel because every step depends on the other. And we can actually overcome that with convolutional networks, because during training we can process all time steps in parallel. So we apply the same convolutional filters, but we do that at each time step, and they are independent, and we can do that in parallel. During testing, let's say in sequence-to-sequence manner, our encoder can actually do the same, because there is no that dependence on the previous output, and we use only our input tokens, and we can apply that convolutions and get our hidden states in parallel. And during testing, one more good thing is that GPUs are highly optimized for convolutions, and we can get a higher throughput thanks to using convolutions instead of RNNs. And you can actually see a table here, and it shows the model based on LSTM and the model based on convolutional sequence-to-sequence. And you can see that convolutional model actually provides a better score in terms of translation quality, and it also works 10 times faster. So that is a pretty good thing, because for real-world systems like, let's say, Facebook, they need to translate the posts when you want, and they need to translate it fast. So in order to implement this machine translation in production environment, maybe CNN is a very good choice. By the way, this paper is by the folks from Facebook. Okay, so let's look at one more thing. You know that when you do sequence-to-sequence task, you actually want your encoder to be bidirectional, so that you look at the sequence from left to right and from right to left. And the good thing about convolutions is that actually you can make that convolutional filter symmetric, and you can look at your context like at the left and at the right at the same time. So it is very easy to make bidirectional encoder with CNNs. And it still works in parallel. There is no dependence on hidden state here. It just applies all of that multiplications in parallel. Okay, so to move further with let me remind you, we are actually reviewing intent classifier and slot tagger, and to move further we need some data set so that we can use it for our overview. Let's take ATIS dataset. It is Airline Travel Information System. It was collected back in 90s, and it has roughly 5,000 context-independent utterances, and that is important. That means that we actually have a one-turn dialog, and we don't need like a fancy dialog manager here. It has 17 intents and 127 slot labels, like from location, to location, departure time, and so forth. The utterances are like this: show me flights from Seattle to San Diego tomorrow. The state-of-the-art for this task is the following: 1.7 intent error and 95.9 slots F1. So this is pretty cool. Another thing is that you can actually learn your intent classifier and slot tagger jointly. You don't need to train like two separate tasks. You can train this super task, because it can actually learn representations that are suitable for both tasks, and this time we provide more supervision for our training, and we get the higher quality as a result. Let's see how this joint model might work. It is still a sequence-to-sequence model, but this time we use, let's say, a bidirectional encoder, and the last hidden state we can use for decoding the slot tags, and at the same time we can use that to decode the intent. And if we train this end-to-end for the two tasks, we can get a higher quality. And notice that we have in the decoder, we have hidden states from encoder passed just as is, and this is called aligned inputs. And we also have C vectors, which are attention. Let's see how attention works in decoder. Let's say that we have a time step E, and we have to output our new decoder hidden state SE. And that is actually a function of the previous hidden state, which is in blue, a previous output, which is in red, and hidden state from encoder, and some vector, which is attention. Let's see how attention works. The vector attention, Ci, is actually a weighted sum of hidden vectors from encoder. And we need to come up with the weights for these vectors. And we actually train the system to learn these weights in such a way so that it makes sense to give attention to those weights, to those vectors. And the coefficient that we use to define what weight that particular vector from encoder has is modeled as a forward network that uses our previous decoder hidden state and all the states from encoders. And it needs to figure out whether we need that state from encoder or not. You can also see an example of attention distribution when we predict the label for the last word. And you can see that when we predict the label like departure time, our model looks at phrases like from city or city name or something like that. Okay, so we can also see how our two losses decrease during training. And during training we use two losses and we use a sum of them. And you can see the green loss here is for intent and the blue one is for slots. You can see that intent loss actually saturates and it doesn't change, but blue slots, blue curve continues to decrease, and so our model continues to train because that is a harder task than intent classification. Okay, let's look at joint training results on the 80s dataset. If we train slot filling independently, we have slot F1 95.7. And if we train our intent detection, our classifier independently, we have intent error 2%. But if we train those two tasks jointly using the architecture that we have overviewed, we actually can get a higher slot F1 and a lower intent error. And a good thing also is that this joint model works faster if you use it on mobile phone or any other embedded system, because you have only one encoder and you reuse that information for two tasks. Okay, let's summarize what we have overviewed. We have viewed at different options for intent classifier and slot tagger. You can start from classical approaches and go all the way to deep approaches. People start to use CNNs for sequence modeling and sometimes get better results than with RNN. This is a pretty surprising fact. You can also use joint training and it can be beneficial in terms of speed and performance for your slot tagger and intent classifier. In the next video, we will take a look at context utilization in our NLU, our intent classifier and slot tagger.